We're going to continue now with the second part of our Bootcamp 3 for using Excel and VBA to solve chemical engineering problems. And the theme of this particular screencast is going to be solving differential equations. We have an approach that we're going to introduce for doing that on a spreadsheet, which is somewhat simplified, but in many cases is perfectly adequate. So what we're showing on this slide is the scenario for a single differential equation in terms of a dependent variable y and an independent variable t. And this is the derivative is equal to an arbitrary function involving y and possibly t. And there's an initial value here stated as 0, but it might be a different value like y0, okay? And then what we're showing is the use of the Euler method to approximate the solution to the differential equation. And here's our solid line here represents the true solution, which we assume exists, although we don't know what it is. And then what the Euler method does is it takes an initial value and the derivative at that initial value and uses it to project a straight line over a small interval of t in order to obtain an approximation of the solution. On the figure here, we've exaggerated the fact that this approximation creates an error between the estimate and the true solution. And then the solution techniques proceeds from this point with the next straight line estimate based on a value at y1. This would be y1, and goes for another interval, which is typically the same width, but doesn't have to be, and it provides the next approximation. And as this goes on with our exaggeration here, the error between the true solution and the approximation can actually grow. Of course, one could imagine that, for example, between 0 and t1, if I used 100 small intervals, then the approximate solution might be following the true solution very, very closely. So the comments here are that the Euler method, although it's fairly simple to implement, it includes errors that accumulate as the solution proceeds. The errors are reduced as our step size, the interval between times, decreases. If we go to very small step sizes, it increases the computational effort, or speaking in terms of a spreadsheet, may take up an unmanageable number of rows on the spreadsheet, and eventually may lead to round-off errors, although with Excel's storing of numbers to 15 to 16 significant figures, that may not be that serious a consideration. And also to mention that there are more complicated schemes, and you may have seen these or used them with other software packages such as MATLAB or Python, that examples being the Runge-Kutta multi-step schemes or the predictor-corrector methods that control error better, but for us they're much more difficult to implement in Excel because they require some significant programming in VBA. And the matter is that we can essentially get away with the Euler method for perhaps most of the problems that we encounter in chemical engineering, certainly not all, but most. So what we're going to do is take a look at an example, a simple example, of an isothermal batch reactor where we have two components named A and B converting to C with a rate constant K, and the rate of disappearance is described by a second order reaction, so that disappearance of the concentration of A is minus our K value times the concentration of A and B. And then we have initial conditions so that we can solve this problem, where we have an initial value for A and B, and perhaps we could have C, but we might have that as being 0. And this example is simplified from a more complicated reaction system that we'll deal with a little bit later. So we have basic data from the literature of the value of K given in units of moles per liter and minutes. And we have an initial condition of a concentration of A and smaller by a third concentration of B and no C. And then we note that by stoichiometry, we can always calculate B from the amount of A that has been consumed, subtracted away from the initial value of B, and similarly for concentration of C. Now, when dealing with systems of differential equations, we like to describe the systems in a graphical way using what we call an information flow diagram. These diagrams have been around for decades, and they help us organize the differential equation solution and make sure that all the information required for the solution is available. Now, for this particular example, the information flow diagram is quite simple in that we have our differential equation, which requires a knowledge of K, and then we are able to solve that, in this case using a numerical method like the Euler method, to obtain values of the concentration of A. From that, using stoichiometry, we can get our concentration of C and B if we have our initial values, and then that feeds back into, for A and B, into our derivative for the concentration of A, and everything hangs together in the information flow diagram. So what we're going to do now is proceed to show how we set up the solution of this quite simple system on the spreadsheet, and then we'll move on to a more realistic, more complicated example that will follow the same pattern. So let's go over to our Excel spreadsheet here. And you can do this too. We're going to open a file which is called batch reactor single EQN starter. And it looks like this. And all that we've really done here is we've established our basic data and operating conditions, and we've established an interval for the Euler method of 0.1 minutes. And we have named all these cells according to the labels to the left. So that has gotten us started. And then what we're going to do is we're going to come over here and we're going to put in some labels for time. CA, CB, CC, And then we're going to have our rate of change, dCA dt, in a fourth column. So let's just center those up. And then we're going to start our simulation with time equals 0. And we're going to put in our initial conditions. So we're going to use a pointer formula up to CA0. And likewise, a pointer formula to CB0. And a pointer formula to CC0. And having that, we can now describe the rate of change of CA at time equals 0. It's going to be equals minus K times the current value CA times the current value of CB, and that is our rate of change. So now what we need to do is, this being our initialization row, as it were, we need an operational row, and we'll put in a formula here that's equals up plus dt. That takes us to our next time. And then we get to this point, and we're going to implement the Euler method by saying that the current value of CA is going to be equal to the prior value, okay, plus the rate of change of CA with time times dt. And that gives us the next value. And then we want to know what is the value of CB, all right? And that is going to be equal to CB naught minus, and in parentheses, the amount of A that has been consumed. So that will be CA naught minus the current concentration of CA. And then our CC, all right, just to be general, will be equal to the initial CC, which happens to be 0, plus the amount of A that has been consumed. So that's going to be CA naught minus the current value of CA. Okay. And then this formula is already operational, so I can just copy it down one, and it gives me the next rate of change, okay? Now, with this formula here, I can drag copy that down to get additional times. And what's of interest to me here, because of some knowledge of this system, is that I'd like to take the solution out to 20 minutes. Now that's a bit awkward. It's going to take dragging for a while, but let's do that and see where we get here. Okay, we're about halfway there, so let's go to about row 200. Okay, so I'm going to take it down to 20, all right? Control-Shift Home. Take us back to the top. And then since this is a set of operational formulas, I can just double-click the fill handle, and I get my solution described all the way out. Now, I can always come in and reformat these a bit just to make them look a little better. But this is essentially what we have for our solution. Of course, as with most of solutions for differential equations, we want to see what that looks like graphically. So I'm going to do that by selecting the entire table, including the headings, with Control A, tab and back tab to get back to the top. And then insert a chart, which will be just straight lines. And I get my initial chart here showing the progress of the reaction. And to work with it a little bit, I'm going to right click and move it to a separate sheet, which you know we do frequently. And then we'll work on this a little bit just to make it look somewhat better. Let me take this axis here, go to the Home tab and increase that to 14 and format it. Format the axis so that it shows number with 3 digits. Make sure that is solid black. And so this is going to be our concentration. And then for the moment, let me take this axis and just bring it up to 14 and make it black. That's going to be our time in seconds. Now, one thing, we notice that we have a legend here. Let's make this a little bigger just so it's easier for all of us to see, which shows our colors, and it shows that this particular curve is the rate of change of Ca. Now that is a different item than the others, which are concentration. So if we select that, format data series, and say we would prefer to have that be on the secondary axis, then we can have a secondary axis which has different units than the primary axis, which will always be concentration, okay? So that might be typically done with solving differential equations. We note here that we can say that we just like the solution out to 20 minutes. That spreads it out for us. And then we can take our legend and say that we want it over on the right. I thought we did. Then we can format that a bit by having a white fill and surrounding it by a black border. At that point, we can take our legend here, want the scale to the right here, we can reformat that to 14 and make it black. Maybe stretch the graph out just a little bit now. And then I won't bother with a chart title at this point. I'll just delete that. But let's put some axis titles in. So we will go to chart design, add chart element, axis titles, primary, horizontal, and that will be time in minutes. Bring that up to 16 point and black. And then it's overlaying our chart down here, so let me raise that a bit to make room for it. And then coming back to our chart design, add chart element, axis titles, primary, vertical. This is concentration in moles per liter. Okay. Make that a 16-point font, black, and squeeze our chart a little bit to make room for that title. I've got these numbers over here, which are rates. So I can come and add a title there. Axis title, secondary, vertical. And I can, for instance, just put in dCA by dt in moles per minute. Once again, increase that a bit. And now I've got something that's more presentable. If I would like, I could pick these and make them a little bit thicker. And now we're depicting the solution to our differential equation. Now, of course, I'll just mention that this is a live solution. So if we were to, we do note it in our chart that the concentration of B starts at 1/3 of that of A and goes to 0. And then the A is depleted, the concentration of C is built, and our rate gradually goes to 0 from negative as we go through this because there's very little B left. I can note that it is a live solution, so if I were to change the 14.7 to 25 and come back and look, we'd see that things happen much faster. If I were to change that to 5, we would note that things happen much slower and more time is going to be required to consume all of the concentration of B. So that's just an example of how we can go about solving a single differential equation with a couple of algebraic relationships going along with it to model a simple batch reaction system. So let me save this, do a save as, and I will take out the starter and instead I will put in the word finished in the file name and we'll save it, okay? So that's an example. Let's go back to our slides and review that, and then we'll move on to a more complex situation. So this is the original setup, and then we have set up headings for the solution table. In this case, we're in a different row than the one that I used, but that's the same setup that we used. This is the starter file that we used. And the Euler method has the CA at Ti plus delta T equal to the CA plus the rate of change times delta T. And so we create an initialization row of the table. And these are the formulas that are associated with that for the rows shown. And then we create the first operational row, sorry about that, with our time, incrementing our time, doing the Euler method projection, putting in our stoichiometric relationships, and copying down the first rate to the second rate. And then we can have our complete solution, and in this particular case, we've created a chart that just shows A, B, and C and does not include the rate of change, which I did in the example that I showed you. And this particular solution, as shown here, is shown in the spreadsheet, which is called Euler method, okay? So having seen that, we're going to go on and look at a sort of the big brother of that example, and this denoted here. And this is a reaction system which is a real one, and it's taken from the literature quite a number of years back, and the references are shown on the bottom of the slide. Now the names of the components, actual components here, such as tricarbomethoxybenzene, are a bit long to be considered used in our nomenclature, so we use A, B, C, D, E, F to indicate those. And we're now talking about 3 reactions instead of just 1. These are shown in the upper left here. A plus B goes to C and a byproduct F, and then C recombines with A to give D, and D recombines with A to give E, and we have production of this byproduct F along the way. And when we now want to write differential equations for that, they're more complicated because we have A being consumed by 3 reactions. This is still isothermal. B by the first reaction. We have C being consumed by being produced by the first reaction and consumed by the second. And we have D being produced by the second reaction and consumed by the third. With a little bit of work here, it turns out we do not need to write a differential equation for E, although we could, but you can compute E using reaction stoichiometry, and the expression for that is shown there in the middle of the slide. And also, the amount of F produced turns out to be just the same as the amount of A that has been consumed. The rate parameters K1 through K3 taken from the literature are shown on the right-hand side of the slide, and the initial conditions turn out to be the same ones that we used for our prior simple example. All right? So that, again, this being more complicated, we want to see how this system is organized. So what we're going to do is we're going to depict it in an information flow diagram, which is more complicated than the first one. And we don't show all the constant parameters needed here, but we show how all the variables are required and can be interconnected with information flow. So how the solution of the 4 equations with A through D, for instance, can go back around and we can compute E and F from stoichiometry, and then we have the information needed in order to describe and compute all the derivatives, which we will then solve using the Euler method. So let's go back over to the spreadsheet and show how we can expand, all right, our previous solution to tackle a system with multiple differential equations using a very similar approach. So back to the spreadsheet, and let's open a file which is called Multiple Reactions Euler Method Starter. Here it is. So what we've done is we've started by creating an empty table here, and we now have described our 3 rate parameters. And you'll note here that we've given these names K underscore 1, etc., because you cannot use names like K1, K2, and K3 because they correspond to cell addresses over here. And then we have our initial conditions just as before. And again, we've used underscore here. It's not necessary in this case, but we've used it. And then the final thing is that we have the knowledge that as time proceeds for this reaction, which actually runs out to about 500 minutes, the rates of reaction slow way down. So in order to keep a good approximate solution, we start out with a fairly fine time step, 0.1 minutes, as shown here. And then later on, we expand that to 1 minute, 5 minutes, and 10 minutes. So let's show you how we go about solving this, and then we'll jump to solution which already has had the work done to create a chart, because we don't want to take all the time to do that here. So we start over here with time equals 0, and then we want to know our initialization row, so we do equals for A and point to the initial concentration of A. Initial concentration of B. And although the next two are 0, we're going to be general about it by pointing to their initial values up here. Okay. Whoops. Then we want to know what are the values of E and F, and we can use the stoichiometry for that, all right? And if we pop back over to our last slide and maybe back up, well, we see it here. The numerator has A naught minus A minus C minus 2D all over 3. See if we can remember that. So it's equals numerator A naught, right, minus value of A, right, minus current value of C, minus 2 times the current value of D divided by 3, I think, isn't it? Okay, so that is our current value of E, which is 0, but we now have an operational formula. And then for F, that's going to be equal to the initial value of A up here. Let's try that again. Initial value of A minus the current value of A, which are the same right now, but that will change. Okay? So that takes care of that. And now what we want to do is we want to take a look at our derivatives. And this is going to be equals, all right, for A minus K1 times the concentration of A times the current concentration of B minus K2 times current concentration of A times current concentration of C minus K3 times current concentration of A times concentration of D, right? Gives us our first rate, which looks familiar to what we had before. And then we want to know what it is for B, so let's hop back and look. B is just the minus K1 CACB, so that's equal to minus K1 times current concentration of A times current concentration of B, like so, okay? And then C, all right, take a peek at that. It's production K1 CAB minus K2 CACC. So it's equal to K1 times CA times CB, that's what's produced, minus K2 times CA right? Finally, the rate of change for D, peeking at it, is K2AC, K3AD with a minus. So it's equal to K2 times CA times CC minus K3 times CA times CD. And that's 0 right now. So this is our initialization row, and we're using the same approach we used last time. So at this point, I'm going to put in a formula here, equals up plus dt1. That gives us 0.1. And then we're going to use our Euler method, which says equals take the previous value times, plus the rate of change of A times, and what I'm going to do here is I'm going to just say times A10 minus A9. The reason I'm doing that is because that interval is going to change on us as we move through the solution. Now, one thing that I can do looking at this formula again, if I edit it, is to say that when I copy this formula, I want the B and H to change, but I don't want the A10 and A9 to change, at least not for column A. So I make that $ A10 using F4 3 times and $ A9. And the reason I'm doing that is then I can drag across and get the rate of change for each one of my components A through D. Now, E and F are stoichiometric, already operational, so I can bring those down. Let me reduce that because those numbers are quite small. And then the derivatives are operational, so I can copy them down. All right. So now I have my operational row. So you'll notice that I wanted to go from 0 to 50 in 0.1. So that's going to take a little bit of work, I think, isn't it? So let's just drag down for a while and see where we get to at 100 about. Okay, we got there. All right, so that takes me 0 to 50. All right. So if I get a hold of this column without this one to the left and double click the fill handle, this gives me my solution all the way down to 50. And then at this point, if I do equals up plus, right, dt2, that gives me 51. And again, that's where now the interval is 1, so it's important that this value here be according to the change in the left 2 rows. So I take this guy here, let me just bring it down 1, and that carries it down to there. And then I can have this, and I want to go 50 to 100. How far did I get? Let's go up to 100 here. Okay. And let me get this and double click the fill handle. This takes the solution down to 100. And then we want to go with dt3 from 100 to 300. So let's go down and set that up. So I'll say equals up plus dt 3. Let's take this down to, I think what we said was 300, right? Is that what we said? Yeah, to 300, and then 300 to 500 is by 10. So let's go down to 300 here. Keep going. So that's going down to 300. It's a little bit tedious, but you see what we're doing here. And double click our fill handle to carry that solution down. And then finally, we're going to go equals up plus dt underscore 4. And we're going to go to 500 with this formula. So let's go down here. Okay, down to 500, all right? And you can see how the time interval has increased as we've gone along, and this has been done with some knowledge of the problem that we're solving, okay? So this takes us all the way through, and then at this point in time, what we can do is we can grab this part of the solution all the way down, and we can create a chart. And I'm not going to go through the details of that, but what I would like you to do is open a spreadsheet, which is called Multiple Reactions Euler Method. So this shows the same setup all the way to the end, and now it's taken the time to create a chart of the results, and we see color-coded all 6 of our components. And just a couple of observations here. We have the A initial charge depleting but not going away. The B, which was our initiator from our first example, is gone in 20 minutes, just as we saw happen there. And then we have the C comes up and maxes out and goes away. The D comes up, right? And then we have our F byproduct, which just continues to increase. And so what we could say here is, well, if we were operating this and we wanted to run the reactor until we have, let's say, the maximum concentration of D, we'd look in here and say, well, that occurs at about 150 minutes. But we've got something that we can work with now, and this represents a solution of 4 simultaneous differential equations with 2 associated algebraic relationships from stoichiometry using the Euler method, all right? Now, the one thing that you can see is that because the rate of change is much slower out here than it is here, we're getting enough accuracy in our Euler method solution, and we have the advantage that we haven't had to use as many rows on the spreadsheet. We used 620 rows or so on the spreadsheet, whereas if we had kept 0.1 all the way to 500, that would have been 5,000 rows, which would have worked, but we don't need that, so we made some judicious choices of time step. Okay, so that is that particular example. Let's go back to our slides and review it, and then we're going to introduce additional examples to round out this particular screencast. All right, so for the moment I can close this because I didn't do anything with it. And then this one here, we made it, it's the same as the final one. I'll just leave it here for the moment. And let's go back to our slides. So this shows what we did and provides the making of the initialization row, and then the operational row, and how we use that for the with the Euler method. In this particular case, for the Euler method, I used the DT1 symbol instead, and that means that I then have to carefully change that to DT2 when I make that transition, but it still works. And we've got our differential equations, and here we've got the stoichiometric relationships. We did that. And then this is the full solution that we have. And this is the chart that we discussed, which is available in that particular workbook. Okay? So this gets us a little bit farther in terms of working with differential equation solutions where we have initial values. Now we're going to look at a different situation we have, and we're going to throw a couple curveballs at this. Number one is we're going to deal with a second order differential equation. We don't deal with those that often in chemical engineering, but they do occur when we have diffusion or we have conductive heat transfer, but we rarely see differential equations which have higher order derivatives. That's not the case for civil engineers, which can end up with third or fourth order derivatives in structures models. But here we've got just a generic second order equation in terms of a dependent variable y and an independent variable t again. The second curveball is that in order to solve an equation like this, you need two conditions, and typically two initial conditions. But what we've said here is we have an initial condition for y, and instead of an initial condition for the derivative, we have a requirement for a condition of y when t equals 10. So this is called a split boundary value or a two-point boundary value problem, and we're going to show you how we can solve this using Excel. So the first technique that is used commonly here is that instead of one second order differential equation, we decompose it into two first order differential equations, because we know how to solve a pair of first order differential equations, and on the spreadsheet how to solve them with the Euler method. And the way we do that is we create a new variable y1, which is equal to the derivative of y with respect to t. And that gives us a differential equation in terms of y and y1. And then we substitute y1 in this equation for y here and here. And we get a second ordinary differential equation, first order, in terms of y1 and y. And then we've got our two conditions. So the strategy that we want to use for that is to try to solve it as an initial value problem by estimating a value for y1 at time equals 0, where you'll recall y1 is actually the derivative of y with respect to t. If we have a value for y1 and y, then we can solve this with initial value here, and we can solve it to y equals 10. But the problem we'll run into is that the value of y will not be equal to 8 then. So we have to come back and we have to change our estimate of y1, solve it again until we meet this condition at the end, all right? And so that's called a shooting strategy, and we're going to show you how we can set that up and accomplish that on a spreadsheet by combining our use of the Euler method and the use of the solver, all right? So let's come back to our spreadsheet, and we're going to open a workbook that is called Second Order ODE Starter. Okay, so this is set up a little bit more for us to give us a head start. And what we've got first is we've got a little inset here with our equation typesetter to remind us what the equations are. And we have our time, all right, here, and the time goes down to 10, but we're doing it with very small intervals to maintain accuracy, so it's actually 1,000 rows, all right? But we've got a big spreadsheet, and that was handled here by putting first a column, counting column from 0 to 1,000, and we have over here our basic data. We've got our initial value of y, which is named y0. We've got an initial value for y1, which in this case is set at minus 4.41, and I'm just going to change that minus 4.4. And then we have a dt value, which we showed here, which is 0.01. Our final time is 10. Our value for y that we want at the final time is 8. And the final calculated y is mapped from the solution, but currently is equal to 0. So our error is 8. So let us set up the spreadsheet for solution here. At time equals 0, we want initial condition for y, so let's point to that, okay? And initial condition for y1 is this one. And then we want our derivatives, so dy by dt is just equal to the current value of y1, and dy1 by dt is equal to 1 by 4 times the current value of y1 plus the current value of y, okay? So that is our derivative there. And then we're going to come down and we're going to do our Euler method and say that we have equals the previous value plus the derivative of y times dt. And this is going to be equals the previous value plus its derivative times dt. Okay? And then these are operational, so I can copy them down. And then these here, I can do the same thing and double click the fill handle, and we have the solution all the way down. Okay? So what we're going to do now is we're going to make a plot of our solution, just the solution versus time. And so let's insert a chart, straight lines, and we've got this going on. Let me move this to its own sheet. And I'll format it just a little bit so things are easier to see, but I won't overdo it here. This is 16, and then these here, make them 16. Okay. And so, and we're only going out to t equals 10, so let's make that maximum 10. And let's make the legend a little bigger so we can see it here. So it's got the y value as the blue line, and it's got the y1 value as the red line. And what we're really interested in here is what happens to the y value, because it's supposed to be equal to 8 at time equal 10. Well, it's equal to something close between 5 and 600, so that's not getting it done. So we're going to come back to our sheet and say, what would we do to try, and by the way, here it shows it's 538 and our error is minus 530.2 between that and 8. So what we would like to do here is say, what can we adjust so that the calculated final value of y is equal to our desired final value of y. And we would do that by making appropriate adjustments to our initial value for y1, which is equivalent to the initial value for the derivative of y. So we're going to do that utilizing the solver, and here to the solver and say that we want, our objective is going to be the final value of y, and we would like that to be equal to 8 by changing the value of y1, okay? And then usually what we do here is we add a couple constraints where we say that this value of y1 has always to be less than minus 5, just to keep it in the ballpark, and the value has to be greater than or equal to, I think I may have set that up wrong, greater than or equal to minus 5. And then this one here, we want this to be less than or equal to minus 4 on the number line. So we have a couple of constraints in there, and let me just check a couple options here just to make sure that we're okay with this, and click OK, and then we're going to see whether it can solve this problem. And now the YF calculated is equal to 8, so let's accept that. And one thing we'll notice here, this turns out to be a very sensitive problem when it comes to the value of y1. And if we look at some more decimal places, we see that. And of course, because of the way this is mapped, if we go to the bottom, we see that our value down here is virtually equal to 8. And then we have prepared charts here that now show what has happened with this solution. And we see that our true y solution takes a dip from 5 and then comes up and hits 8 on the mark, whereas our y1 solution is shown here on the right, and it starts down here on this scale here, which is about minus 4.4, whatever it was, and it comes up and it takes on this value. But the one we were interested in is y, which now meets the conditions that we were after, okay? So let us come back to our slides now and review that. This was the initial solution that we set up, and it has shown that our value of 8 for y is not met at all, because we're up here, in this case, between 3 and 350. And so if we involve the solver as we did, we find out we can meet that condition, and then we end up with the solution being correct, okay? So that takes us now to 8. So that is a couple of things there that are important to realize. Number one is how to go about solving a second order differential equation. Okay, that's the first thing. And then the second thing is how to, and it could be more than one second order. You just have to decompose each one of them into 2 first orders. And then how to meet a split boundary value condition by computing the solution with an estimate of an initial condition and then using the solver to converge the initial so that it meets the final condition. We're going to move on to a final example here in this screencast for differential equations. And it has the characteristics of the previous example, but it's more applied and also has some differences. And we're not going to build this from scratch, but we're going to show you how the solution is set up and point out some characteristics. And you have the workbook file available so that you can look at it along with me. All right. So this is a tube-in-tube heat exchanger where the fluid flow is countercurrent. And we have cold fluid moving through the inner tube and hot fluid through the outer tube. And this is governed by 2 differential equations. And these are linear differential equations, but the characteristic that makes it interesting is that we know the temperature of the cold fluid as it enters and the hot fluid as it enters down here. But in order to solve the system moving forward in distance, we have to have an initial condition of the outlet temperature of the hot fluid, and that is something that at least for starters we have to estimate. Also, this heat transfer model is set up so that energy is conserved as it transfers from the hot fluid to the cold fluid. And what you will notice is that the sign of the temperature difference is the same in each of these differential equations. And that may look a little bit unusual to you, but the reason that comes in is because of the direction of the fluid flow of the hot fluid, which enters a sign change of minus Z here and reverses the original temperature difference, cold to hot to cold. Also, for energy conservation, the heat transfer coefficient here based on inside area and the heat transfer coefficient based on outside area are related as a single overall heat transfer coefficient, and the relationship is given over here using the ratio of the diameters. So moving on here, there is a slide with all the nomenclature that you need, and we're not going to go through that item by item, but it's there for your reference. And then we repeat the equations here and we indicate that what our conditions are, where this is an initial condition at Z equals 0, and this is a final condition at Z equals L. And so the strategy we use here is to estimate the outlet temperature of the hot fluid, which occurs at Z equals 0, solve the equations to Z equals L, and compare the hot temperature that we get at Z equals L to the requirement of the inlet temperature, and then readjust our initial estimate of the hot outlet temperature until we get a match. So that is somewhat similar to what we did with the previous generic example of a second order equation, but this is more applied. So we have some basic data and operating conditions here where we're choosing to use actual tubes and not pipe, and as a result they have a precise outside diameter of 2 1 inches and an inside diameter based on the gauge, 11 gauge of the tube. And then the length of the tube is heat exchanger is 5 meters, all right? And we have our operating conditions of the hot stream coming in at 50 and the cold stream at 10. We're using water here with density and heat capacity, and then we have flow rates of 1 liter per second and 0.3 liters per second for the cold stream, and we've estimated a heat transfer coefficient HI based on SI units. Okay, so that's what we have there, and we're going to pop over to the spreadsheet now, and we're going to open a spreadsheet called Countercurrent Heat Exchanger, XLSM. All right, this is a macro-enabled worksheet, and you'll see why later. And it looks like this, so you can see that we've done a lot of work in setting up for the solution of this, and we'll review it with you now. First, over on the left here, we have our specifications and operating conditions. So down the far left, we have our tubing specifications, and let's just open that up a bit, and actually calculate more specifications from the basics than we need. But we have an outer diameter of 2 inches, and then we convert that to meters, and this for the outer tube likewise. And then we have an inside area of that tube, all right? We have the inner tube with its outside diameter converted to meters, and its ID to meters, outside and inside area, and then we have the length of the tube. And in most cases, wherever you see a symbol here to the right, we have used that symbol to create a name for that cell. And then we move over here, we have the density of the fluid, which has a name density, heat capacity, which we call C sub P, and then we have our flow rates, 1 liter per second, and we convert that to cubic meters per second, use the density to get the mass flow rate, and likewise for the tube flow rate. And then just for curiosity, we compute the linear velocities, and you can see that both of them are around 1 meter per second. So it's taking about 5 seconds for the fluid to flow through the 5 meter length of the heat exchanger. And then we've got heat transfer coefficients here, the 5,000, then converted by the formula to the HO. And we have heat transfer areas per unit length, and you'll always notice that this is area per unit length, so the net units are meters, but it's meters squared per meter, and it's equal to the circumference of the tube, pi d, all right? And then we have our inlet temperatures, 50 for the hot inlet at the end, and 10 for the cold inlet at the beginning of the heat exchanger. And then we move over here and we estimate the hot outlet temperature as 40 degrees because we don't know exactly what it's going to be. And then we set up a table to solve the differential equations. similar to what we have done in the past examples. In this case, we set up an index from 0 to 100, and then we use the distance as the index divided by 100 times the length of the heat exchanger, and we get the distance down the heat exchanger in units of meters, all right, but essentially it's 5 centimeters per step. This gives us our Z value, and then we start out as before, and this is the initial condition for the cold stream. This is the estimate for the outlet of the hot stream, and then we compute our derivatives according to the differential equations that you've seen. And then moving down to the next row, we establish the Euler integration formula as the previous value of the cold temperature plus the derivative times the difference between this distance and the one before. And we do the same thing for the hot, all right? And then, as you might expect, as we move down the heat exchanger, the cold stream is heating up, right? And also the hot stream is heating up because it's flowing in the opposite direction. And then if we go to the bottom of the solution down here, we see that the final value of the hot is 47 degrees, and we know that the inlet temperature there is supposed to be 50 degrees, so we do not have the correct solution. So we come back here, and in this case we compute an air squared term, which is the difference between the specified hot inlet temperature, 50, and that final value of the hot temperature computed. Do the difference of that squared, all right? And that is just a choice that we've made. And then we can go to data solver, and this is set up to solve the problem. And what it's got here, the objective is the air squared term. It wants to minimize that by changing the hot outlet temperature estimate. So if we click solve and accept that, we find that the error is now 0, that estimate for the hot outlet temperature is 42.1, and if we look at the final temperature for the hot stream where it comes in, we see that it is now 50, so we have solved the problem, all right? And so that's how this is set up. It's a very similar approach to what we used for the 2-point boundary value problem with the generic equation in the previous example. And here we can create, and I already have created a chart tab, and so you can see what the solution looks like, all right? And it's got the cold stream coming in at 10 degrees and ending up at 36 to 37 degrees. It's got the hot stream coming in precisely at 50 degrees and ending up at about 42 degrees. And of course, if we go back now, and if we were to make any changes with the temperatures or with the flow rates, then we would get a different solution. So for instance, if I came back here and I increased the hot flow rate to like 1.2 liters per second, all right, then I now have an error, all right? So if I look at my chart, I see that I've had not met that 50 degree requirement here anymore. So I come back and I go to the solver, and I have to do this each time. Data solver, solve. And now the error is back to 0, and we have a different hot outlet temperature that's been determined, and we have slightly different curves based on the fact that we increased the flow rate of the hot stream. And you can see that my arrow up here that I placed manually doesn't quite line up anymore, okay? And then we can go back and change this back to 1, and we can go to our solver again and solve. And then we're back to where we started with the solution, okay? So this pretty much completes that. We're going to add a feature that you might find interesting. So we'll go back over to the slides and carry through this now. So this indicates the workbook we're using and shows the rows on the left side of the worksheet with their specifications. And then this shows the starting point with an estimate of that 40 degrees, and it doesn't quite meet the 50-degree requirement down here, and we have an error. So we have set up to minimize the error squared by changing this, and when we run the solver, it solves the problem, okay? And then we have this chart depicting the solution. Now, another thing that we can do here is that we can take that operation of running the solver, and we can record a macro, all right, that tells us how, from VBA, how we would run that solver solution. And if we pop back, there's something you need to know here, because otherwise, if you attempt to do this, it will not work. So let's come back to our spreadsheet and go over to VBA, where I have already recorded the macro. And the thing that you need to know here is that under Tools and References, you have to have the solver selected as one of the references. Otherwise, the macro, you can record it, but it will not run. And there's one other feature that we have added here to the solver solve statement, and that's user finish equals true. So let me show you why I did that by removing it for now, all right? And then let's come back over and let us start again with 40 degrees, so we've got an error. And now, instead of running the solver from the menu, all right, if I do an Alt F8 to see my macros and just look at the one from this workbook, I see that I have the macro that solves this, and I can run it. And then it shows me this solver results, and it solved the problem. So that is using a macro to run the solver instead of using the menu to do it. And that's, you know, the one thing that I had there, and let's come back over, is that I added here a specification, user finish, and when you're setting a specification, it has to be : equals true. Okay, so if I add that and come back over and do an Alt F8 to see my macro, let's get on here. Alt F8 and run it. It runs, but it doesn't show that final dialog box where we have to accept the solution, because by now we know generally that the solving thing is going to work. And then the final little feature that we've added, if I go to my view zoom, and instead of 130 zoom, if I go to 120, is you'll see that there is a button that shows up over here. And that's a button that I have added so that if I put 40 degrees in here and click solve, it runs the macro and it solves the problem for us. And that's just like in the previous example way back where we added the little checkbox. You can add a button on the worksheet that runs the macro, and we show how to do that on the slide. So let's go back over there. So here we showed that you had to set up references, all right, for this. And when you are running some of these procedures from VBA, you may have to enable references. Another example of this is if you are using any of the data analysis tools, such as the regression tool, and you want to do so from VBA, you have to set up the references so that it will work for you. So here we showed that we added this user finish equals true, all right? And you might wonder, well, how did we ever figure that out? And that is available if you are looking for help on the solver from a website called solver.com, because the solver is not a piece of software provided by Microsoft. It is provided by an outside vendor, okay? So you can look up, there's a lot of information about the solver on the website solver.com. And so then what we did was we added a button on the spreadsheet by going to the Developer tab, the Insert and Form Controls, and picking the upper left thing, one for button, assigning it to the macro, and it shows up on the spreadsheet. And then we changed the caption here by scrubbing across it from button 1 to solve. Okay, so we come back over. How we added that particular button over here. And you can customize the font a little bit and make it bigger or have a color or whatever, but we're not taking time to do that here. Okay? So that brings us to the close of this particular segment of Bootcamp 3 for Excel and VBA. And in the next screencast, we will be looking at techniques for optimization and for curve fitting or regression, which are similar procedures. But for this point, we bring this screencast to a close.